All right, let's get right into it. We're going to be talking about one of the most essential tools in all of science and engineering, vectors. But hey, don't let that word scare you off. At its heart, a vector isn't some super complex math concept. Just think of it like this. It's an arrow on a map telling you exactly how far to go and which way to point.
So let me ask you a question. If I say I'm in my car driving 60 kilometers an hour, can you tell me where I'll be in an hour? The answer is nope, not a clue, right? I could be 60 kilometers north of here or south, or maybe I'm just doing circles in a parking lot. You've got the how fast, but you're totally missing the where to. And that right there is the problem.
And this simple idea gets us to the core difference. That first number, 60 kilometers per hour, is what we call a scalar. It's just a number, a how much. But that second description, 60 kilometers per hour north, well, that's a vector. It's got the number, the magnitude, and the direction. It tells you the whole story. See, to really describe pretty much anything that moves or has a direction in our world, just knowing the speed isn't going to cut it. We need a better tool for the job. And that amazing tool is the vector. The absolute easiest way to think about a vector, it's just an arrow. That's it. The length of that arrow, that's its magnitude, its strength or its speed. And whichever way the arrow points, well, that's its direction. Pretty simple when you think about it like that, right? So, we've been introduced. But now let's see how these new arrow numbers actually work. And here's a little spoiler for you. They don't exactly play by the same rules as the math you're used to. Okay, let's picture this. You're going to take a little walk. You start right here, and you walk 3 meters to the east. We can draw that out as our first vector, an arrow that's 3 units long, pointing straight to the right. Got it? Now, from the very tip of that first arrow, you make a sharp left and walk 4 meters north. So let's draw that second vector, starting right where the first one ended, making it 4 units long and pointing straight up. Now, your brain might immediately go, okay, 3 plus 4 is 7, but just look at where you are. You're definitely not 7 meters away from where you started. The actual distance from where you started to where you ended, what we call your displacement, is the straight line connecting those 2 points. And when we draw that arrow, look what happens. We've made a perfect right-angled triangle. A little trip back to high school geometry, and the good old Pythagorean theorem tells us that this final arrow, your true distance from home, is exactly 5 meters long. Now, what we just did by drawing those arrows has an official name. It's called the triangle law of vector addition. It sounds fancy, but all it really means is that if you line up your vectors head to tail, the arrow that goes from the very beginning to the very end is your result. That's it. Okay, so that's how we put vectors together. But what if I told you that the single most powerful, most useful skill you can learn in physics is actually how to take them apart? And I'm going to be real with you. This next part, breaking a vector down into what we call its components, this is the spot where a lot of people get a little stuck. But stick with me here, because once this clicks, I promise, everything else with vectors just falls right into place. Let's think about it like this. Imagine you've got a little remote-controlled car, and it's zipping diagonally across the floor. That single diagonal path is a vector. But you can also think about its movement another way. At any given moment, it's also moving a little bit to the right and a little bit forward all at the same time. And that leads us to the big question, right? When we see that diagonal arrow, can we figure out exactly how much of that journey is purely to the right and how much of it is purely up? So how do we do it? Think of it like casting shadows. You've got your main diagonal vector. Now, if you shine a really bright light straight down from the ceiling, the shadow it makes on the floor, that's its horizontal component. We call it A sub x. Then, if you shine a light from the side, the shadow it casts on the wall is its vertical component, or A sub y. And here's the best part. We don't have to guess how long those shadows are. There's a formula for it. If we know the length of our main vector, let's just call it A, and we know the angle it's pointing at, we can find the exact lengths of those shadows using a little bit of trigonometry. The horizontal part is always the length, A, times the cosine of the angle, and the vertical part is the length, A, times the sine of the angle. These 2 little formulas are your secret weapon for breaking apart any vector you find. So think about what we just did. We basically pulled off a bit of mathematical magic. We took one kind of tricky angled problem and broke it down into 2 super easy straight line problems. And that technique is the key to solving a huge amount of problems in physics and engineering. All right, so we can add them and we can break them down. But what about multiplying them? Well, it turns out there are 2 completely different and really cool ways to do that.
Okay, first up, you've got the dot product. You can think of this as the agreement product. When you do it, you don't get another arrow. You get a single number, a scalar. And that number tells you how much two vectors are pointing in the same direction. Then, you've got the cross product, which is a whole different animal. This one measures the twist between two vectors, and the answer is a brand new vector that points at a right angle to the first two. It's basically the math of rotation.
And trust me, these aren't just some abstract math ideas. In physics, when you want to calculate how much work you do by pushing something, you use the dot product of your force vector and the distance vector. And the cross product, that's what makes the world spin. It's the principle behind torque, which is the reason a wrench tightens a bolt, a door swings open, and a fan's blades spin around. So there you have it. We started this whole journey with a simple question about a car on a map, and we've ended up with the actual mathematical tools that describe everything from a casual walk in the park to the fundamental forces that make things spin.
So we've seen a vector is really just an arrow with a size and a direction. We've learned how to add them together, head to tail, and most importantly, how to break them down into their simple up, down, and left, right pieces. So I'll leave you with this question. Now that you know what you're looking for, where else can you spot a hidden vector at work in the world around you?